Okay, so we have seen that the probabilistic interpretation of the scattering theory, we have seen that the scattering for a scattering cross-section can be defined in terms of the number of particles measured by the detector at a given direction divided by the density of incident particles, number of target particles, and the velocity of the incident particles. Now let's see how we can calculate this in terms of the matrix elements that can be calculated in our field theory. Now what we will be looking at is we have, let's say that we have some target, and this is B. We will be sending some wave packets. Representing our A particles. And these particles, they will, each one of them will have some impact parameter, and they will be scattering of our of the target, and some of them will go to our detector. And what we will be trying to do is we will try to calculate the number of particles detected in the detector per second, so that we can derive the cross-section from that expression. Now first let's write down our initial wave packets. Initially, let's say that we have one A wave packet and our target wave packet. So first, rather than writing this two particle wave function, let me write the one particle wave function. So it will be a superposition of various momentum eigenstates. So we had already defined the annihilation and creation operators for a definite momentum, let's say call it K, acting on the vacuum. And you see here we are actually using the empty state, because what we will be eventually doing is at minus infinity, we create this phi A, phi B at minus infinity, and then we just evolve it in time for a total duration of t minus t. So we create this state at minus t, which eventually we will take to minus infinity. We let it evolve, and after the evolution we will ask for the amplitude that this initial state evolves into a final state which will contain n particles. So this is what we are trying to calculate as a first step, because once we have this matrix element, then we can calculate the number of particles that will scatter in our particle. Now usually we can also write this in a Heisenberg picture as we have a phi A, phi B particle. This is the ingoing particles, so initially. Now in the Heisenberg picture the states don't evolve, and then we are looking for the overlap of this in state with state and particle state at the outgoing states. So these two things are equal. So to calculate this matrix element, first let's write what our single particle state is. So it's a superposition of various momentum states. Each one of these momentum states will have some weight. This is the momentum state wave function of, let's say, of our A particle. And then of course we have all possible momenta. Of course, in an actual experiment, what we will do is we will be creating these beams with a almost precise momentum. So this psi A particle, psi A k wave function is peaked near k is equal to, let's call it PA. So this is a scattering process in which we have the PA and the A particle with a momentum PA and B particle with momentum PB, let's say forward momentum. These will scatter into some final states with momenta PF. But of course, in a realistic case, the beams will be somewhat localized, the particles, and hence their momentum cannot be unique. they will be written by a superposition of particles. The wave function will be peaked around this value, and the spread of the wave function around this value will be the uncertainty in its momentum, and the size of this beam, the bunches in the beam, will determine the uncertainty in the position. So the Heisenberg's uncertainty principle tells us that these two uncertainties should be larger than some non-zero value. So with this in mind, so this is our this is our A state. Let's look at the normalization of this phi A first. So we will be needing the normalization of this psi A momentum wave functions. Now the state phi A, it will be normalized to 1. If it is normalized to 1, then we have if you write each one of the bra and the ket in terms of these states, 0, or let me write take the integrals out, d cubed k1 divided by 2 pi cube. Let's say k1 is the integral corresponding to the bra, and then we have the d cubed k2. This is the momentum, this is the integral corresponding to the ket, and we have psi a star k1, psi a k2, and the matrix element of phi k1, phi dagger k2, right. Now to calculate this matrix element, we can just write, let me write it explicitly. This is equal to 0, phi of k2 dagger, phi of k1, plus their commutator, phi of k1, phi dagger of k2. Now this annihilation operator acting on the empty state will give me 0, and also this creation operator acting on the bra will also give me 0, so there is no contribution from this term. And this commutator, we had already seen that it is given by 2 pi cube Dirac delta of k1 minus k2, the three-dimensional Dirac delta. So, and using that the vacuum is normalized to 1, this matrix element that we are trying to calculate is 2 pi cubed Dirac delta cubed, the three-dimensional Dirac delta of k1 minus k2. So you see that this three-dimensional Dirac delta, using this three-dimensional Dirac delta, I can calculate the k2 integral, and this 2 pi cubed will cancel the 2 pi cubed in the k2 integral, and after the k2 integral, wherever I see k2, I should put k1. So this tells me that this one over here, should be equal to, well, there is only a single k integral left, so I will just call it k. I have the k over 2 pi cube times, now due to this Dirac delta, after the k2 integral, I know that k1 is equal to k2, so this is the absolute square. So here I have psi k absolute square. So this is the normalization of the momentum state wave function that we use to define our state phi A. Now note that this phi A, phi B, and these final state particles, we can also make similar definitions. So with these similar definition, also to save some notation, I will just use this in and out notation. I will in fact stick with this one. Later on I will convert to this in and out state notation. So this matrix element that we are looking for can be written in this form. So we have this phi 1 up to phi n, these are the particles. I have the evolution by 2t, then I have the ingoing particles. Although we are assuming that we just have two particles colliding with each other, you can if you like, you can just generalize this to more than two particles. The final state will be more than, it can be, the number n can be arbitrary. So this will be equal to, for the ingoing particles, I have the integrals over d cubed kx divided by 2 pi cube, where here x will be a or b, and I have the corresponding wave functions. Then I have for the outgoing particles, let me just label them by f from 1 to n. I have their corresponding integrals kf divided by 2 pi cube. And then I have phi f kf star, since these are the bras, they are conjugated. And inside I have vacuum phi k1 phi kn e to power minus I h 2t phi dagger ka, this is for the A particle, phi dagger for the B particle, kb. As you see, this matrix element is already in the form of the matrix elements that we had studied before. And in fact, after this, in the next video, we will relate the scattering cross-section matrix elements to Feynman diagrams. So to simplify the notation, let me just make one definition. I will define the single particle states, let's say k, as square root of 2e, the energy corresponding to k, phi dagger k. Okay, so let me change. Here we are actually considering a single particle, but this derivation can be generalized to an arbitrary number of particles. So I have a single phi operator, phi k acting on vacuum. Now the reason why we define this square root of 2ek is such that this k prime is now 2ek Dirac delta cubed k minus k prime. So this form is valid in every reference frame. Even if you change your reference frame, this form will still stay as it is. So with this convention, we can write this matrix element. So phi 1, phi n, out states phi a, phi b. In state, this is equal to, well, I have the x from a for the integral of the a and b particles, d cubed kx divided by 2 pi cube, phi x kx, f from 1 to n, d cubed kf divided by 2 pi cube, phi f star kf. And here I have okay, since I have this normalization, here I have to divide by that normalization, divided by 2ex kx, and each one of these is divided by 2e kf. And here I have the k1, kn, this out state, and I have Ka, Kb, the in state. So this is actually the matrix element of states of definite momentum, but in reality we have these wave packets, so this is why we have all these integrals appearing over here. And this matrix element is actually defined as what is known as the S matrix element. S of the Ka, Kb to Kf. This is matrix element is defined as out K1, Kn, Ka, Kb in. Now you see, whenever you are scattering, let's say, two particles, as in this case, it is possible that those two particles can miss each other, and in that case, the only that would appear that in that case the out state will be just exactly equal to the in state Ka, Kb. And that is not what we are actually interested in. What we are interested in is actual scattering processes. So usually the T matrix is defined as S is equal to the identity matrix plus I times T. So here S is a matrix whose matrix element is defined in this form. If we take out this identity, describes the processes in which nothing changes, essentially no scattering. and this T will contain the dynamics of the system. And before continuing, let me also make one correction. So here for the in states, you see this psi A, we said that psi A k is peaked around k is equal to PA. Its Fourier transform, the position space, will be peaked along this line. So psi A of k actually corresponds to B is equal to 0. So I will define this particle with an impact parameter B as the translation of this. And in order to translate this in the B direction, what we do is we just need to multiply it by e to power I B dot k. So this wave packet is describes a wave function whose momentum wave function is peaked around PA, and its position space wave function will be peaked at an impact parameter B. So analogously, I need to add a correction over here. There is an e to power I B dot k. This is ka, and keep in mind that B here if we again choose this direction to be the z-axis, B is in the perpendicular direction to z. So this is our matrix element. Now let's look at the number of particles that will be scattered. Now before looking at the number of particles that will be scattered in the direction of my detector, let's look at the probability. PB. Now the initial state, this is the state I create in the experiment. Now if I have my detector, let's say this is the scattering center target. My detector is over here. It will detect all the particles with definite momenta in this cone. So in this solid angle d omega. So what I will do is I will calculate this scattering matrix element into a definite final states of definite momenta. So this is the corresponding amplitude, this is the out. And to calculate the probability, I just need to take the absolute square. But keep in mind that these states ki, they are not normalized to 1. And to calculate the total probability, my detector will not measure just a single k1. It will measure all the particles that scatter into a momentum within a volume in momentum space of t cubed k divided by 2 pi cubed. And also let me divide by ek. Let me call this ekf for all the final state particles. So this is the probability that my initial particle, phi A and phi B, when they scatter, they will scatter into a final state k1 kn with momentum k1 kn within a volume in momentum space given by d cubed kf. And this 2ekf is from here, because we are not normalizing it to a single Dirac delta. There is a 2ek factor, and this d cubed k over 2 pi cubed factor is from the fact that this psi wave functions are normalized with the momentum space wave functions are normalized with a 1 over 2 pi cube. So this is my probability. Now if I'm interested in the number of particles scattering into my detector, this will be equal to the probability that a particle with a given impact parameter will scatter. Now in my beam I have all kinds of particles with various impact parameters, but of course it's a two-dimensional vector. And then I need to multiply with the density of the particles multiplied by L not A particles. You see, and A is the volume density. So the density of particles that will hit a given area will be given by NA times L, the beam length. So this is the NA times LA, if you like. This is the density per area, per cross-sectional area. Now if we are interested in the number of particles per unit length, let me just put a VA over here, per time. For the time being, let me just put LA. Now let's calculate, let's write this out explicitly. The number of particles hitting my detector will be equal to d squared E. Well, let me also, I will assume that within the scattering region, the density is constant. So this is divided by NA times LA. Since I assume that it's constant, I just took it out. Now this probability will be, I have first this, let me just denote that by d gamma, where this d gamma is the phase space of the final state particles. This is our d gamma. Now let me write this matrix element over here. I will have integrals over these wave functions of the ingoing particles. So let me write it as d cubed ka d cubed kb. Well, since there are, I'm taking the absolute square, there will be two of them. Let me denote the conjugates by prime. And divide each one of these comes with a factor 2 pi cube. Then I have the A particle with a moment, the wave function of the A particle. I use the notation psi. Ka, psi A conjugate Kb. Ka prime, psi A for the B particle, Kb, psi B conjugate Kb prime. Then what else we have? There is the K1, Kn, this is the out, Ka, Kb in, multiplied by K1, Kn, this is the out, Ka prime, Kb prime, conjugate, and then I have e to power ib Ka minus Ka prime. Now, again, let's continue with our, we said that this out, K1, Kn, Ka, Kb in will be given by the matrix element of this T, since we are not interested in the non-scattering process. T of Ka, Kb scattering into Kf. And note that this overall we will have an energy momentum conservation. So this will be proportional to 2 pi to the 4, Dirac delta to the 4, Ka plus Kb minus Kf, and the proportionality constant we will call I times m. This is our scattering, invariant scattering amplitude m. So in terms of this invariant amplitude, we have d and d divided by NA LA. This is equal to, let's say, d gamma I will just put one integral sign, and then I have okay, d cubed ka, d cubed kb, d cubed k prime a, k prime b divided by, also here I forgot to write, there is a, due to the normalization of these ka and kb states, let me write it over here, 2e ka, 2e kb, 2e k prime a, 2e k prime b. So here I have 2 pi cube square root of 2e ka, 2 pi cube 2e ka prime, 2 pi cube 2e kb, 2 pi cubed square root of 2e kb prime. And then we have okay, this matrix elements 2 pi to the 4 Dirac delta 4 ka plus kb minus the square root of kf, the other Dirac delta to the 4 ka plus kb minus square root of kf. These are for the prime. By the way, kf's are not prime because they are the same kf. We are not integrating over that. And then we have im and minus im prime. Well, this m prime is with the momenta ka prime and kb prime. And then we have the wave functions psi a of ka, psi b of kb, psi a of ka prime, psi b of kb prime. Okay, the primes are with the conjugate. And well, okay, I have the b integral, but keep in mind that the b integral actually will give me a Dirac delta. So here I have two b's, so that here I will get two Dirac deltas, 2 pi squared Dirac delta. This Dirac delta will make sure that the perpendicular components, the components perpendicular to the z direction of ka and ka prime should be equal. So this is the number of particles that will be hitting my target. And well, now let's try to evaluate these integrals. Now, using this Dirac delta, we can already integrate the two of the components of ka prime. So this will be equal to, well, let me just write down. Okay, so there will be a couple of approximations we will do. First, we can evaluate this ka prime, two of the components of this ka prime. Second thing to keep in mind is that we will be, note that these wave functions are quite peaked, close to a definite momentum. So psi a is a peak function which is non-zero only in the near vicinity of pa, and it is zero everywhere else. But if you look at functions of ka like this one, it is a continuous function of ka. So at all the points in which psi a of ka is non-zero or significantly different from zero, E of ka will be actually equal to E of pa. So using that approximation, I can just replace all the ka's appearing over here by pa, kb's appearing over here by pb's, and take them out of my integral. So let me do that. Of course, I cannot do that at this moment for these Dirac deltas, but I can do it in these energies, and also I can do it in these matrix elements. So this number, this ratio becomes d gamma I have a 1 over, let's say, 2 pi cube, 2 pi to the, let me write it, 12, 2e of PA, 2e of PB. You see this 2e of PA is from this 1 over square root of 2e Ka and 1 over 2 square root of 2e Ka prime, because both psi A and psi A star, they are peaked around PA. So this is PB. And I will take these M out. Here this M, let me write it explicitly, M is the matrix element for the process PA plus PB. Took one particle with momentum PA, the other particle with momentum PB. They collide and they scatter into a final state with particles having momentum PA. Absolute squared. So what remains inside is, I have a 2 pi squared, this one over here, or in fact 2 pi squared. Now let me write the integral. I have d cubed Ka, d cubed Kb. I evaluated two of the integrals of Ka prime, so that will give me the Ka z only, d cubed Kb prime, psi A of Ka, psi B of Kb, psi A star of K1 prime, psi B star of Ka prime. This is Kb prime. But from this point on, I will assuming that Ka prime perp is actually equal to Ka perp. And so I wrote the wave functions. This measures is written. Well, I have the 2 pi to the 4. The 4-dimensional Dirac delta of Ka plus Kb minus sum over Kf. 2 pi to the 4. 4-dimensional Dirac delta of Ka prime plus Kb prime minus Kf. And this Dirac delta is gone. I have already evaluated it. There is a 2 pi squared. Now let me look at the integral of dkaz and dkbz. And I will use this Dirac delta over here. So d cube K, this is prime. So this is prime, this is prime. Now this Ka prime appears only over here. So I will just take the 2 pi Dirac delta Ka z prime plus Kbz prime minus this Kfz. And then I will also take the energy. 2 pi Dirac delta Ea prime plus Eb prime minus Ef. Now I can evaluate this Kbz prime integral using this relation, the first Dirac delta. So that would give me dka prime z 2 pi squared Dirac delta. Ea is, well, let me just leave it as Ea. Ea is square root of Ka prime squared plus Ma squared. Well, although we are looking at only a single particle, I mean, this derivation can be also a single type of particle. This derivation will also hold for different types of particles, Kb prime squared plus Mb squared minus sum over Ef, with the understanding that Kbz prime is equal to Kf minus Kaz prime. Now this Dirac delta can be simplified. It will be just the k is a z prime that makes this equal this 0 divided by the absolute value of the derivative. Now if I take the derivative of this argument with respect to ka prime, I will get here ka prime z divided by ea prime minus this minus sign is due to this minus sign over here between the kbz in the definition of the kbz prime, in the expression of kbz prime in terms of kz prime. So minus kbz prime divided by eb prime. Well, the momentum over the energy is just the volume, the velocity. So this is 2 pi squared divided by v corresponding to ka prime minus v corresponding to k prime a b. And so if you go back to our expression, now our expression can be simplified further. You see this became now d gamma. This is the phase space of the final state particles. Oh, I forgot the Dirac deltas. So this becomes d gamma 1 over 2 pi to the power 12 to E of Pa to the energy of the B particles. Our matrix element squared. Now d cubed Ka still remains, d cubed Kb still remains. Now we had evaluated this Ka z and Kb z integrals, Ka prime z and Kb prime z integrals. They gave us 2 pi squared divided by v Ka prime minus v Kb prime multiplied by the remaining Dirac deltas and the wave functions. And we have the 2 pi to the 4 Dirac delta to the 4 Ka plus Kb minus this Kf, and then we have the other 2 pi to the 4 Dirac delta. We already used 2 of these Dirac deltas over here. What remains? Dirac delta squared Ka prime per plus Kb prime per minus Kf, and there is a d squared k. There is another integral over d squared, the remaining components of kb. And keep in mind that Ka prime per was already Ka per. And using this Dirac delta, there's a 2 pi squared. Now using this Dirac delta over here, we can calculate the Kb prime per integral. And that would give us d gamma 1 over 2 pi to the power 12 2ePa 2ePb m squared. Now let's see, this is in fact 2 pi squared over here, 2 pi squared over here, This is also squared. 2, 4, 6, 10. So we have just two factors of 2 pi squared left. Here we have m squared. And what is left? We have d cubed ka, d cubed kb. Now if you would keep track of the momenta, you see ka already ka prime and ka prime perpendicular component of ka prime and ka, they should be equal. So this is actually psi a of ka squared. And similarly for kb, psi b of kb squared. And what remains is we have the Dirac delta to the 4, ka plus kb minus sum over kf. This Dirac delta we had already used to evaluate this d squared kb prime integral. And let's take one more step further. You see these, again, I will use the approximation that this will be approximately equal to wherever, since these are highly peaked, I can replace the ka appearing in all the other functions to be approximately with pa. pb m squared. So I have this Dirac delta to the 4, pa plus pb minus kf. And if I make that approximation, then again here I have 2 psi a ka squared integrated over ka. That just gives me a 2 pi squared, 2 pi cubed, and similarly for the kb integral, that's 2 pi cubed. So this cancels 2 of these, and so we have d and d, the number of particles that is scattered into my detector through a beam of length La with a volume density of Na, is given by d gamma 1 over, I also had a factor of v. Here I also use the same approximation. Wherever I see a ka prime or kb prime, I put pa and pb, so divided by va minus vb. 1 over 2e pa, 2e pb, and then I have m squared divided by va minus vb, and then I have 2 pi to the 4, and the 4-dimensional Dirac delta of pa plus pb minus sum over the final momentum. Now if you remember our definition of d sigma, this was equal to the number of particles in the detector per unit time, this is the difference, divided by Na, the volume density, the number of A particles, the number of B particles, and the speed of the A particles. And if Nd is not the number per second, but actually the total number, then this Va is actually multiplied by, is replaced by La. So in our case, we are just considering a single B part, single scattering center, so Nb is 1. So this scattering cross section is, let me write the final state phase space explicitly, dpf, d cubed pf divided by 2 pi cube. Well, here kf was the final state particle momentum, but since I'm using the pa and pb to be the average approximate values, I just converted the notation to pf divided by 2e, the energy corresponding to that particle, times 1 over 2e pa, 2e pb, VA minus VB times m squared times 2 pi to the 4 Dirac delta to the 4 PA plus PB minus PF. You see, this is the initial flux of the particles, so how many collisions we have per second. This is the phase space of the final state. This 2EPF is due to the normalization of the states that we used in calculating this m squared. And this m squared contains all the dynamics, and the overall energy momentum conservation is what appears over here. So our actual task will be from the dynamics calculating this invariant mass squared term.